I want today to derive the center of mass of a solid cone. So that's what we will be doing for today. Recall what I talked about center of mass, which is basically the point from which we can consider motion to be taking place at of any object, that at that point the center of mass is where everything is centered, and that is kind of where the path of motion will take place. So if we have cone, something like that, let's draw one out. Let's draw a circular cone. So let's draw a cone. We'll give it radius r. Give it radius big R like that. And then we'll put it on an axis like that. Put it on an axis. And we'll give it height h, something like that. Okay, perfect. And give it the height of h like that. Now, to find the center of mass, it has to be along the axis here. It has to be along our y-axis. So we're not going to integrate with respect to x at all, we'll integrate with respect to y here. So it has to be somewhere along this axis. We don't know exactly where it is, so we can just define it something like that. Let's use a different color, just a blue, to define this space. Define that space dy. Define the little disk dy. And you'll have to deal with the fact that I can't draw, so you'll have to imagine it to be a disk like that. Okay. This disk has a certain depth to it. We'll call it y, like this. So that's some height y. And then it also has some radius. We'll call it little r, like this. We'll call that little r. Okay. And so, via similarity, we can show the following to be true. Okay. So, you can kind of see similar triangles are being formed. You have two parallel lines, and we can talk about how that is related. But it's something like this. Y to r is proportionate to, of course, h over big R, like that. Okay. And we'll come back to why I stated that proportionality later. Now, that's just something to keep in mind. And of course, if we solve for the little r in this expression, we know we solve for little r, which ends up being r times y divided by h is equal to little r, like that. Okay. Now, we want to find the volume of this particular disk here. Okay. The height is dy, And the area will be determined by pi r squared, which is area of a circle, because it's like an imaginary disk. So the volume of this strip, which we'll call dV, the dV for little volume will be the area of the strip times dy. And in this case, the area of the strip is pi little r squared, and we defined the little r to be r capital R y over h. Okay. And so if I plug it in, so pi times r over h squared dy until we end up with pi r squared y squared divided by h squared dy is equal to dV. Okay? And that's our volume of our little strip. Now, what we need to do now is compare the volume of the whole to the volume of the little piece here. And this is how we will find the center of mass. In other words, we need to find the mass of this little bit of this strip here. Okay? And we do that by using the density of the whole cone. Okay? If you need to look at it, please come back to this piece. I don't want to erase it all. Okay. And so let's clear it. Okay. So we need the density of this cone here, like that. So I'm going to redraw my cone. And we found, of course, the volume of the strip here, like that. It's kind of not perfect. It is supposed to be symmetrical, but of course the artist here is not a very good one. So now, this is R, this is Y, of course. Now, we need to find the mass of the strip, of this kind of disk, like that. How we do it, of course, is by using the density of the entire cone. And so we'll use this density. So Greek letter rho, the density of the cone, is the total mass of the cone, divided by its volume. Okay, well, that's the density of the cone. Now, the density, because it's a solid cone and it's uniform throughout, the density at any given point will be exactly the same. So, therefore, we can state density of the cone is equal to the change in mass over the change in volume. Okay. From that, we'll solve for the change in mass. So the m is equal to density of the cone, density of the entire cone. So these two will be the same, and times the change in volume. Okay. Now, the change in volume We already found it. We already found what that change in volume was. Recall that this dV is pi r squared y squared divided by h squared, like that. Okay. And so we replace it times dy. So we replace the dV here in our expression with our dV. So dm, see the density of the cone times, of course, the dV. We'll put in parentheses pi capital R squared y squared divided by h squared dy. Okay, everybody following so far? Now that we have this expression here, we can use this to find the center of mass for us. Okay, so the center of mass will be related all by this equation here. Center of mass integral of y dm, right? So, right, it's somewhere along this y point. So this is how we relate it. The sum of the integral of that. Oops. Okay. Now, this dm, we found out what it was. So it's going to be 1 divided by m integral of y multiplied by our dm, which is density of the cone multiplied by pi capital R squared y squared divided by h squared. Okay. Times dy. And anything, since we're only integrating with respect to the y-axis, or in this case x-axis technically, but only integrating with respect to the y variable, anything that is not y comes out of this equation. So let's hijack it and take it all out. So everything that's not y, density is a constant, pi is constant, r is constant, h is constant. We'll take it all out. So this becomes 1 over m, and then everything that comes out, density pi r squared divided by h squared. Then we're left with the integral of y squared times y, which is y to the third, dy. And we're going to integrate it with respect to the height, because this is the y-axis here. So we're integrating it with the whole, right? Because we want to find the center of mass of the whole thing. So it will be from 0 to h. So we integrate it from 0 to h. Okay. And from here, that integral is very simple. Right? So it's y to the 4th over 4 from 0 to h of the rest of that madness. Okay. And so it becomes big R squared, e squared divided by m. Alright, and so we plug it in h, we get h to the 4th. So I'll write that on the page. So this becomes the density times pi capital R squared divided by mh squared. So all equal to the y center of mass times h to the 4. Okay. So nothing too complicated here. Now we have to take the density of the cone. The density of the cone is the mass divided by the volume of the cone. The volume of the cone is 1/3 pi r squared pi r squared h. So volume of the cone pi r squared h, like that. And so if I manipulate it algebraically, we can do m times 3 divided by pi r squared h, which is equal to 3m divided by pi r squared h. So we take that and plug this in for the density of the cone. Okay. So our y, center of mass, is equal to 3m divided by pi r squared h times pi r squared divided by m h squared, should be little h by the way, times h to the 4 over 4. Okay. Now we start playing, canceling stuff out. Pi r squared kills the pi r squared. Mass kills mass. You have 1, 3. That kills that. We end up with 1 left over. So center of mass for the y is 3 height divided by 4. With respect to the top of the cone. If it's with respect to the base, it is 1/4. Okay? 1/4 of that. Now, let me finish that. Okay? This is with respect to the top of the cone. Okay? Or you can say 1/4 height with respect to the base of the cone. Now, and that should make sense. Why? Because of the way the mass is distributed in a cone. Less of it, more of it is closer to the bottom than it is at the top. So it would make sense that because of the shape, it's not evenly distributed. There's more onto than is in the other. So that's why we have it like that. Okay.